on this computer. Okay, so today's session is really meant for to review some of the basics. It's a fairly small group, so feel free to ask questions. Can someone just say something so I can make sure I can hear the sound?
Hello.
Okay, great, good. I just want to make sure. So either feel free to type into the chat. I'll try to monitor the chat if you have a question, or just feel free to unmute yourself and ask a question. Okay. I just want to make sure the sound was working. Let me just make sure the recording's working. So everyone good. Okay. So these are the things I'll plan on going over at a bare minimum. We can always go over more if people have questions or if you have specific questions. The session is designed to be useful to you. So first of all, we're going to review some of the concepts that you saw in class, but it's always helpful to see them again, especially if you're fairly new to this. So we're going to look at what an impulse response function is and why it's useful. We're going to spend some time looking at how you take a signal and would expand it or write it in terms of weighted and shifted delta functions or impulse responses. Sorry, that should be impulse responses or delta functions, that's right. And then we're going to describe and apply the definition of a linear system, describe what's called the superposition principle, and describe and apply the definition of shift invariance, get into convolution, and talk about convolution in general. Okay. Now, if we have time and there's interest, we can certainly spend some time getting into Fourier transforms, but the next supplementary session, which will be 2 weeks from now, will delve more deeply into Fourier transforms for those of you who would like some review of that. Okay, so impulse response, as discussed in class, is basically we're looking at the response of the system to an input of infinitesimal width and unit area. So for example, here we have on this plot here, we have two little impulses here, okay? And so you can imagine those are little dots that you might want to image. And then the images you get are over here. So these are the blurred images that you would get. Okay, let's see if I have a pointer here. Okay, I think I can use my hand as a pointer. Yeah, so these are the blurred images here, okay, on this side here. And so the basic idea is that if we know the response to any little dot, and if the system is linear, then we can get the responses to the two dots by just adding up the responses to each of the dots. And that would be then our linear system. And if we can make that assumption, it makes our lives a lot easier. Okay. So these are some examples of what you might do. So for example, Dr. McVeigh in class said that oftentimes in his lab, he just takes a ballpoint pen and snaps off the ball of it and uses that as a very small impulse. You might also, some people sometimes use like a wire. You could use a very thin wire. So that would be an impulse in 2 dimensions. And if you did that and looked at the response to the wire, you would end up with, in this case, it's called the PSF stands for point spread function. Okay, which is the same thing as impulse response. So those are the 2 terms you might hear bandied around. All right. So that's just some example of if you had a very thin wire, that's sort of your attempt to approximate an impulse response. And then when you image that wire, it gets blurred out. Uh-oh, what's going on here? How come I can't do this? Oh, okay. Okay, so the notation we're going to use in class, there's going to be 2 types of delta functions we're going to talk about in class. One is the Dirac delta function, which we'll talk about now. And the other one we'll talk about later is what's called the Kronecker delta. So the Dirac delta function, we're going to need to use that for continuous functions. Okay. And so that's sort of using to try to represent things in the real world where we sort of imagine things are very continuously. The Kronecker delta you'll see later is where we use to model discrete functions. And that's very useful because ultimately we digitize everything. And so, for example, everything just becomes digital numbers and we want things in discrete quantities, okay? So for example, right now, the camera on my computer is taking some continuous image, going into the camera, it's being digitized, turned into numbers. Those numbers are being sent over the internet and they show up on your screen. And then those numbers are then converted into continuous levels of brightness on every voxel of your computer screen. So we have to make this, so essentially we're going from continuous to discrete and digital back to continuous so that our eyes can see it. So the notation that we have is we will typically call it delta of x is our Dirac delta function. And that's a 1D Dirac delta function. We could also have a 2D Dirac delta function. So we could have Dirac delta function in 2 dimensions. And so typically for images, we'll definitely need at least 2 dimensions. Sometimes there's a little square put in front of the delta function just to remind people that it's 2D. We typically won't use that in this class. And so we'll just typically stick with this notation. We probably won't get into too much of 3D delta functions, but you can imagine for a 3D, objects in the world are 3D. And so you would definitely want to have 3D delta functions if you want to represent a 3D object. And then obviously, mathematically, you can go to any dimensions you want, okay? But we'll typically be either primarily in 2D, maybe once in a while we'll go into 3D. Okay, so one of the more important concepts you have to have that will make your life a little easier in this course is to really be comfortable with this idea of what an impulse response is. So once again, as we said, the impulse response is essentially, mathematically, it means I take my Dirac delta function, I imagine putting that into my system, and then I just measure the response to my system, h of x. Okay, so that's all it is. H of x is my impulse response. All right, so that's all that means, is if you put a Dirac delta function into your system, the impulse response is just what comes out. So what that means in real life is, for example, if I had a point object, let's say like a very tiny sphere, I put it into my X-ray system, my impulse response simply is the image of that point object. All right. So now we want to also talk about the system response. We want to say, well, what happens if you just don't put in a point object? What if you put in any image? Like if you put in a heart or a brain or a hand or a leg, that we could represent as some function f of x. Okay. And we put that into our system and our image of that object is then g of x. Okay, so that would be the system response to my object. And so for medical imaging, we want to say, well, if I put in any object, and in this case, even though I'm saying arbitrary object, for the purposes of medical imaging, it's an arbitrary biological object. Later in this course, we'll get into why that matters, because if you know you're only imaging biological things, then you can actually make some assumptions that allow you to go faster or make better images. If you have to assume any arbitrary object, then that's where you have to satisfy different criteria that are quite strict. But let's just say in this case, we're imaging some object, some part of your body, or some biological specimen. We put it into the X-ray system, and the system response then is simply the X-ray image of that object. Okay. So now we want to talk a little bit about, now that we've talked a little bit about the impulse response and the system response, we want to go back and talk about how would I sort of express, what do I think about when I try to express signals, okay? And the two signals that we have to deal with when we're doing medical imaging is we have to think about things that are both discrete Okay. A discrete, for the purpose of this class, just means that you can index the values of the image. So in this case, where the index is n, so that's a 1D image that we're indexing. So there's values at integer values. Okay. So for example, if you have an audio waveform and you just sample it, you have samples at discrete indices, okay, that you would then store in your on your computer or your iPhone. Similarly, if you had a 2D image, like for example, what you're looking at on your screen, your screen is a discrete display. You basically have little voxels in there. And so you need two indices. You need one to go across horizontally, let's call that M, and the other to go across vertically, that would be N, okay? So discrete just means we have integer values for the indices. We're assuming that that there might be a value at 0 and a value at 1 and a value at 2 and so on and so forth. For example, if your screen is 3000 by 2000, then M might go from 0 to 2999 and N would go from 0 to 1999. For continuous time or space, that's typically what we imagine what we're trying to image in the real world. So for example, if you look at my audio, my voice, the sound you're hearing from my voice, we're typically say that's a function of time, where we assume that time can be as small as we want to. Okay, so the idea is that that's some continuous function that we would try to measure or characterize. So most 1D signals, the time is a very common 1D dimension, and we typically think of that as thing, but it could be sort of sample distance along a path. So how far are you going from, say, your apartment to your lab? That distance could be S of X as you're going along. For imaging, we're definitely going to want to be 2D, right? So we imagine objects as a function of both X and Y. Okay, and we assume that X can vary continuously and Y can vary continuously. So the main thing is here, the variables X and Y can vary continuously, whereas for discrete, the variables M and N, we assume are integer values, right? Okay, so now we're going to talk about the other delta function that we talked about, that we mentioned earlier, which is the Kronecker delta function. And compared to the direct delta function, this is a very simple function, okay? It's a discrete function, so it's only defined at integer values. And it's defined as follows, that delta of n is equal to 1 when n equals 0 and 0 otherwise, okay? So if we draw a picture of it here, we can just see that it's 0 everywhere and it just has a 1 when n equals 0. Now, it's also going to be helpful to have shifted delta functions, okay? So for example, this is a picture of delta of n minus 2, all right? And so this has value when n minus 2 equals 0 or n equals 2, okay? So we're going to deal with lots of shifted functions in this course, so it's useful to get comfortable with them. Sometimes students get a little confused. Just always take the argument of the function, in this case n minus 2, and see where it equals 0 or whatever you want it to equal, and then just solve for that if you ever get confused, okay? So for example, if I had delta of n plus 2, that would be a delta function that has value when n plus 2 equals 0 or n equals minus 2. So the way I would draw that would be at minus 2, it would be 1, and it'd be 0 everywhere else. All right. So the same thing in 2D, we can sort of consider looking at delta mn is 1 when we're at the origin, m equals 0 and n equals 0, and 0 otherwise. So this is a picture of delta mn, and it's pretty simple. So we're looking at an image now, and red means 1 and blue is 0 in this case. So let's say red equals 1 and blue equals 0. All right. So let's take a look at one of these. So for example, this one here. So this is going to have value when m minus 2 equals 0 or m equals 2, and obviously when n equals 0. So we look here and yeah, that's correct. That's where it has value at the coordinates 2, 0 is where we have value there. Okay, so you want to be comfortable with shifted delta functions. So the idea is you have a delta function, and then you can have any shifted version of that delta function. Okay, and so essentially we're going to, if we can shift the delta function to any place in space, then we can imagine we're going to just make up our image or our object out of all those shifted delta functions. So any questions up to now? Okay, let's see anything. If you have a question, just put in the chat or just type up. Okay, the next concept that we want to talk about is discrete signal expansion. And so this is just saying if I have any function g of n, okay, so for example, this is some function I just made up, g of n. The claim is I can write that as these are shifted delta functions. I'm multiplying them by some value, and then I'm just summing them up. Okay, so let's see if that makes sense. Let's say that, okay, well, let's say I didn't indicate where 0 was. Let's say this is the 0 point, okay? And let's say this has value 1, 2, and minus 1, okay? So in this case, I could write g of n. There's a delta function at the origin, so that's 1 times delta of n, okay? And then it goes minus 1 at n minus 1, okay? So this has value when n equals 1, right? So we're assuming that this is 0, 1, and 2. Those are the indices, right? And then I have another delta function plus 2 delta n minus 2. Okay, so that's all that means. That basically I can break any function and just imagine it as different delta functions with different shifts. Each shifted delta function is multiplied by a different amplitude. Similarly, if I have a two-dimensional function, then I can have shifted versions of the 2D delta function and here multiplying them by some value. Okay. Oops. Okay, so for example, here's a 2D signal. Let's see what's on the next page. Okay, yeah. So here's a 2D signal, A, B, C, D. And we'll go, for the next one, we'll do the math. But here, we're just showing that, just convince yourself that this 2D image, right, which has 4 values in it, we're assuming it's a discrete image, so it's just got values A, B, C, and D. You could break it into 4 different images. One where there's just A, one where there's just B, one where there's just C, and one where there's just D. And for each of those images, there's only one voxel where there's value, and it's 0 everywhere else, right? So it's pretty straightforward to see that that 2D image is just a sum of those 4 2D images, okay? So how would we write this? And unfortunately, I think I reversed it here. So A, B, C, D is different here. But let's say that this is the origin. So this has origin 0, 0. So that's the coordinates 0, 0. So what is this? This is a Dirac delta function. So this is Dirac delta function Mn, or sort of Kronecker delta function delta Mn. So this image is just A times the Kronecker delta function Mn. Let's look at one other example. So let's say this is B, right? So B times this image here. This image has value, this coordinate here is 1, 0, right? We've shifted 1 to the right and we're still at the 0. So this would be delta m minus 1, n. Okay, so it looks like I got an error here. So this should be actually, because we're doing m and n, yeah. So this actually should be m minus 1, n. Okay. Let's see if I made mistakes on this one. So this is C, right? This is here C times this delta function, which has a value at 0, 1. So this should be Kronecker delta of delta m n minus 1. So this is wrong. N minus 1. And this is fine because it's shifted both ways. So m minus 1, n minus 1, it's multiplied by b, so that's correct. All right. So the bottom line is we can write this function now as this summation, right? Where these take into account all the different shifts of my delta function, and for each shift, I'm multiplying it by some amplitude. Okay. So the math might look a little bit complicated, but if you have this simple picture in mind, that's all you really need to know, that you're just taking a bunch of shifted and scaled delta functions. Okay, so let's do this exercise together. Let's try to write this. So this is some image, let's call it G of Mn. Okay. And let's just, we're not gonna do the whole thing, but let's just do enough such that we figure out what's going on. So this is at 0, 0, right? So we know that this has 7 times my Kronecker delta Mn. Okay. And then this one is at units 1, 0, right? So this would be, we're going to add on 8 times delta m minus 1 n. And then let's look at this one. This is at 1, 1. So that's going to be 3 times delta m plus, oh, so this is at minus 1, sorry, minus 1, minus 1, right? Because we've gone down. That's m plus 1, n plus 1. Okay, and you can sort of fill out the rest on your own as a good exercise. If you can write down what this image is in terms of scaled and shifted delta functions, then, sorry, this is actually wrong. This is at 1, minus 1, right? So this should be m minus 1, yeah, n plus 1. Okay, so if you're sort of new to this would be a good exercise for you to sort of complete and just write out all the rest. And if you have any questions, feel free to let me know. All right. Okay, so we're going to keep going. There's no questions. So the 1D direct delta function is a little bit different. So if you're new to this, it's a little sort of a strange function. Once you see it enough times, you sort of get used to it. But I'm just going to say a few words that to give you some background on that. And the characteristics of the 1D direct delta function are as follows. It's equal to 0 when x is not equal to 0. Okay, so basically it's 0 everywhere except for at x equals 0. But it also has the interesting property that it has an area of 1. Okay, so it's like this infinitesimally narrow function that still has an area of 1. Okay, so we can think of how we would approximate that. We could start off with a function like this. This is just my rect function, rect of x. Okay, so this has value of 1 between -0.5 and 0.5. So that has area of 1 times 1 equals 1. Okay. And then we can just imagine looking at functions rect of x over tau and multiplying that 1 over tau as tau goes to 0. Okay. So it's important to realize that what is rect of x over tau? That's just the rect function with tau. Okay. So we're going to take this rect function and we're going to shrink it so that its width gets smaller and smaller and smaller. All right. But to keep the area of 1, as we shrink it, we also have to make it taller. All right. So the limiting function of a delta, if you take the limit as calculated as 0, that's your impulse, your direct delta function. Because this has area of 1. All right. We can also have a 2D direct delta function, which is equal to 0 when you're not at the origin, but it also still has this property that the area under it is equal to 1. Okay. So we can model this as a 2D direct delta function. Okay. That has area of 1. And then we essentially shrink that width. And as the width shrinks, we have to make the height go up to keep the area 1. So it's going to be it's going to end up as this very narrow spike that just has the area of 1. Now, a super useful fact is that the 2D direct delta function is just the product of the two one-dimensional direct delta functions. Okay, so I'm not going to say too much about this, but just direct delta functions, as you can see, are sort of strange functions. They're really not ordinary functions. They're actually what are called generalized functions, and they're defined by what they do under integral. So you can never really deal with a direct delta function on its own. You always have to see what does it do under an integral. Okay. So that's the most important property of the delta function is actually what's known as the sifting property. And this is something that Dr. McVeigh mentioned in class. All that means is if I take my direct delta function, and in this case, a shifted direct delta function, delta x minus x naught, and I multiply it by any we'll call smooth function. So we'll just assume that the functions we're dealing with are smooth compared to the dimensions of the direct delta. Then that, and I take the integral of that multiplication, then the sifting property says that operation just lets me pick out the value of g at some coordinate x naught. All right. So that means if let's say I have a function g of x, there's this smoothly varying function, and then my direct delta is right here. So that's a direct delta x minus x naught. If I multiply those two functions together and then integrate, then I would get this value g of x naught. So that's going to be very useful for sampling. Right, because sampling means I want to just take values I don't want to know g of x at every x, that's too many numbers. Maybe I want to just sample every centimeter or every millimeter. And then I could mathematically, I can use these shifted direct delta functions to show how I'm sampling that function. Okay, one useful fact is that later on in the class, we will be dealing with scaled direct delta functions. And it just means that this identity is true, that delta AX acts like delta X multiplied by 1 over A. All right, so that's just something to keep in mind. We may not have the proof of that on a future homework, but if you do have the proof, if you do need to do the proof, then you can actually just follow this, okay? Okay, so now let me stop. Okay, let's see, there's something in the question, the chat, okay. Wouldn't this be a volume? Okay, can you clarify what you're asking about? What would be a volume? Oh, for the 2D direct delta function. Okay, so let's go to the 2D direct delta function. So basically, if I draw a 2D function, right, it's got x and y, right? Okay, so it's still a function of x and y, but then the way I imagine is I draw it like it's a 2D function, but it has value of 1. Right, so that's obviously, so the way it's a 2D function in terms of, it's say this is g of xy, right? but the way we draw it is in 3D. Similarly, for a 1D function, right? If I have g of x, right? That's a 1D function, but I'm drawing it in 2D to show the variations. All right, does that answer your question? The other way you can look at it is you can look at it from up top, x and y, and then this is just a 2D function, right? It's just 1 here and 0 everywhere else. Okay, so then I can think about taking the area of this as just 1 times the value here, which is just 1. Does that answer your question?
Can you hear me?
Yes, I can hear you.
But as like x and y, like the like width approaches 0, then it's shrinking and then the height's increasing, right?
The height is the value of the function, yes.
Yeah, so then like the total volume stays at 1, but the area is shrinking.
Well, this is basically, this is what we're calculating, right? We're calculating this, right?
Mm-hmm.
So it's just a matter of when we think of a 2D function, right? It's useful to think of it as integrating a volume, right? But it's still just the area of the 2D. It's still just this double integral of that 2D function.
Yeah, but like a single integral would give you like area under the curve, right? So then a double integral is like volume under like a plane kind of thing.
Yeah, that's right. So, right, you can think of, right, so it's sort of, yeah. So like, yeah, that's right. A single function, you're looking at the area under the curve, right? Yeah, and so then you're looking at you are looking at the volume in this thing, right?
Mm-hmm.
Yeah, so what was your question then?
Oh, I mean, you just mentioned that it's like a constant area, but wouldn't it be a constant volume?
Oh, okay.
Because the height's increasing while
Yeah,
the
yeah.
area is
Sure,
decreasing.
I understand what you're saying. Okay, yeah. So yeah, if you think about it that way, then it is a constant volume. Yeah.
Okay, thank
Yeah,
you.
you're right. Thank you. Yeah. Okay. Thanks for clarifying. Henry, you said, I'm also confused how the integral for direct delta function can equal 1 because I thought the measure at 1 point is 0. Yes, that's a great question. The measure at 1 point is 0, which means by measure, you just mean basically for everyone else, measure is just sort of, the 1 point doesn't take up any space, right? Infinitesimally small. That's why, hold on, let me enable live transcription. That's why these are not ordinary functions. These are generalized functions. So they're not really defined at any point. They're only defined by what they do within an integral. Okay, there are whole books on generalized functions. So obviously we can't really go into that, but that's sort of for this course, as long as you sort of know that's true, what that means is you should always be, when you're asked about, if you're asked anything about direct delta functions, which we probably won't get into too much detail about that. We just expect you to be able to use them. But if you had to do anything to prove anything about direct delta function, typically you either approximate it with a rect function in the limit, or else you look at it and see what it does under an integral. So for example, in this case here, when we want to see what delta AX does, we just put it underneath an integral and see what it does underneath an integral sign. Okay, great. Okay, that's a great question, but and if you're really into math, it's actually a very fascinating area. Look under generalized functions, and you can learn more about that there. Okay, so great questions. Yeah, keep it up. These sessions will be more useful if you can ask questions as they come up, and we really want to gear these sessions to the questions that people have. All right. So if there's no more questions now, I will keep going. From the sifting property, basically, we just want to say we can write a 1D function as follows. G of x is a 1D function. So we can write that as the integral of all these shifted direct delta functions multiplied by the value of the function at the location where that direct delta function is, quote, active. Okay. The intuition behind this is sort of easier to, if you think about discrete. This is sort of in the limit, the sum of these very narrow rect functions multiplied by some value. So basically, we're approximating g of x as the sum of very tiny, these shifted little functions. Now in the limit, they become Dirac delta functions, which we represent as arrows. Okay. So the reason we want to do this is because we want to be able to write any function as a sum of shifted and scaled Dirac delta functions. In discrete time or discrete space, it's just a simple sum. In continuous space, it has to be an integral. Okay. Similarly, for any 2D function, we can write it as this double integral of the shifted Dirac delta functions multiplied by the value of the function at the location where the Dirac delta function is active. Once again, the intuition is you can get it from looking at a discrete sum. You're basically just taking these very narrow 2D rect functions and multiplying them by the value of the function at that location. Okay, so as long as you have that sort of intuitive picture in mind, that will take you a long way. Okay, so now we can go back to look at the impulse response, and we're going to start building up some notation so we can talk about impulse responses in mathematical terms. So the idea is that in general, I might have an impulse here. I have an impulse that forget how to say these terms. Does anyone know how to say, what's the term? Is this xi and eta? I forget how to say the Greek terminology for these. Anyways, these at this location, I have an impulse response. Okay, or I have an impulse at this location. And the impulse response, we will typically use things like h or g as, or typically h is a very common, for this course, we'll use h a lot. So this is just saying that, so in imaging, obviously we have one coordinate system for where our object is, and we might have another coordinate system for where we actually create the image. For example, in X-rays, we would have, your object would be here, the X-rays shine through that, and then the image is made on the X-ray film or the X-ray detector. That's sort of not exactly in the same location, right? So there's one coordinate system here, x1, y1 for my object, another coordinate system, x2, y2 for where I'm actually making my image. So this is just sort of saying that in general, we have to take that into account. So what we're going to say is that my impulse response is going to be a function such that in the coordinate system where I measure it, this is where I measure it, right? These are the measurement coordinate systems. And it also depends on where the impulse was in the object. So these are the object coordinates. Okay. So if you look at the mathematical notation here, this is just my Dirac delta function, 2D Dirac delta function shown at some object coordinates xi and eta. And it's saying if I go into my imaging plane and I look in my imaging plane as a function of my imaging coordinates, I get some response that depends on where the object was originally in the object domain. All right, so that's the general notation. In this course, we're sort of going to try to simplify it so we don't have to carry around all these things. And we're typically going to try to get it such that it really doesn't depend on all, you don't have to keep too much track of where things are. And we'll assume we can make that assumption in a few slides. Okay, so for now, we're going to look at linearity, and there's two properties to linearity for linear functions or linear systems that you'll review. Probably some of you have already gotten this one. Okay, I think the first one is I. Okay, great. So linearity is pretty simple. So here I have an image or an object I1, and it gives me an output k sub 1. Okay, and then I think about another object I sub 2, and my system gives me an output k sub 2. Linearity just means that now let's say I put in my input of I1 plus I sub 2, then if it satisfies addition, then this will be K1, K2, okay? K1 plus K2. So that's, if a system satisfies that property, then it's linear, okay? Some of you might remember this from like linear algebra for like vector spaces, and it's a similar concept. The other property is scaling. All right, here I have I1 and it gives me K1. Now, if I multiply I1 by some scalar A sub 1, then my output should be multiplied by that same scalar. And if it does that, it satisfies scaling. Okay. So we say a system is linear if for two inputs I1, I sub 2, and if with outputs K sub 1 and K sub 2, then I have a weighted sum of those inputs, A1, I1 plus A2, I2, then my output is simply A1, K1 plus A2, K2. So that would be a linear system. Okay, so let's do, I think I have the poll set up. Let me just check for a minute. Let me just, hold on just a minute. Do I have my polls set up here? Where are the polls? Pause recording, live, 1, 2, 3. Huh. For some reason, they're here. They are. Polls. Sorry, polls and questions. Okay. So I'm going to launch a question. So go ahead and take a few minutes and look at this question. And basically, you're asked to figure out if this is a linear system or not. Okay. So this is just totally anonymous poll. So just use this to sort of think about it and then just enter your question in the next minute or two. Just for A, this is just for A, sorry, just answer for A. So a couple people haven't responded, so go ahead and just put in your best guess and then we'll keep going. Okay, great. So everyone's responded, so thanks for responding. This is helpful for me to sort of gauge what we need to talk about. So it looks like 77% of you said yes, and 23% of you said no. Okay, so the overwhelming consensus was yes, this is a linear system. All right, so let's take a look at this. So let's say I have some input G, right? And this says the output is G plus 10, right? And let's say I have another input H, and this would give me some output H plus 10, right? So if I come on with an input G plus H, the output would be G plus H plus 10, right? That's what it says to do, right? Does that satisfy the addition property? Let's check. Well, these two together give me G plus H plus 20. So these two things are not equal. So it doesn't satisfy addition, right? So there alone, it's not linear just from addition. Let's go ahead and see if it satisfies scalar multiplication. So we know that G goes to G of 10. And so 2G would go to 2G plus 10, right? That's what the system says to do. And then, but according to linear scaling, if I multiply G by 2, I should multiply the output by 2. So 2 times that is 2G plus 20. And these two things are not equal either. So it also doesn't satisfy scaling. Okay, so it's basically not linear at all. Okay, so even though it's a very simple example, if you can sort of get what's going on in this example, that's going to be very helpful for you if you have any questions like this on either in this course or other classes. This is a very typical question that could be asked on a, for example, like preliminary exam or some other exam. Okay, any questions on that before we go on? Okay, if there's no questions, let's start the next one. So the next poll is for B. So here I have a function G and the output is 10G, and tell me if this is a linear function or not. Okay, let's take a look at this. So this one, the overwhelming over 90% said yes, so sort of flipped. So so let's take a look at this. So this says we go from G to 10G, right? So if we had H, that would go to 10H, right? And then we had G plus H, that would go to 10G plus H, which is equal to 10G plus 10H, which is equal to the sum of those, right? So it does satisfy addition. Let's say we had 2G, that says we would go multiply that 10, that's 20G, and that equals 2 times 10G, right? So that satisfies scaling. So yes, it is linear. Okay, so that was a little simpler. Okay, any questions before we move on to the next example? Okay, this is the last, I think, one I have for you for this one. Is this a linear system? So now it's a 2D system where any function you put in, you're going to move it up by 1. So up this way, and then move it to the right by 1. So you get g of x minus 1, y minus 1. So think about this and tell me whether you think it's linear or not. Okay, a couple people more to respond. Just take your best guess. Just guessing, even just guessing if you're not sure is better than not responding because it helps your brain learn. Okay, great. Okay, so we've got 62% said yes and 38% said no. So there's a slight, there is a majority, but there's enough that we should talk about this in more depth. So we're going to look at it 2 ways. One is just from the math point of view, and the other is from the more looking at it pictorially. So we know if we have g of xy, that's just going to give me g of x minus 1, y minus 1, right? And if I had h of xy, that would give me h of x minus 1, y minus 1, right? And if I had g of xy plus h of xy, that would just, shift everything, right? X minus 1, y minus 1, plus hx minus 1, y minus 1. And this sum is equal to that. So it does satisfy addition. Okay. Similarly, if I had 2gxy, that would just say shift that function. Okay. And this just as equal to the 2 times, my original shifted function. So this is 2 times that, right? So that satisfies scaling. So it is, yes, it is linear. All right. So you can think about it pictorially. Let's say, this is my g function. I just shifted it. We'll just look at addition. Let's say I had some other function, right? Let's say I had some other function here, right? Let's call this h, right? And then I just shifted that up like this, right? Okay, so I could shift each separately, right? Or if I have both of them together and shift them together, it's the same thing. So the addition property is definitely satisfied. Similarly, if I have this as my g function, I just multiply it by 2, that just changes the brightness of that image, right? And if I shift it, that would just change, then the output brightness is also changed by the same amount. So the shifting doesn't affect that, right? So yes, anytime you do translation, that is linear, which is good because in imaging, you want to do lots of translations typically. So it's good that that's linear. Okay, any questions before we move on? Okay, so this leads us to superposition, which is one of the more important properties. Is the superposition is essentially saying we've shown that we can write any function as a sum of, these are shifted delta functions, and these are the scaling terms, right? And let's say we can write the response to each of these scaled Dirac delta, Kronecker delta functions, okay? So that means that I should be able to, if I look at the linear response to my g of m, right? Then I just put that linear system, I apply it to g naught delta m plus g1 delta m minus 1 plus g2 delta m minus 2, right? Now, remember, it's a linear system. So I have my inputs a weighted sum, right, of things. And so I should be able to write my output as a weighted sum of the outputs to each of these responses. So I should be able to write, since it's a linear system, I should be able to write my output as g sub naught times the response to the first one, right, plus g sub 1 times response to the second one, plus g sub 2 times the response to the last one. Okay, and that's just g0 times h of m prime 0 plus g sub 1 times h of m prime 1 plus g sub 2 times h of m prime 2. All right. So that superposition is just a fairly straightforward application of linearity. Oops. And that's, I've just written it basically in nicer form here. So just so you can follow along without my messy handwriting, essentially, so we got to this point with my messy handwriting, and here I'm just writing it as a sum and sort of writing that explicit sum just using the summation symbol, okay? The bottom line though is if superposition holds, then the output is always going to be a weighted sum of these impulse responses. Okay, so that's very important. That means if I know the impulse response to a function, And any input you give me, I break it up into a sum of weighted delta functions, and then my output will just be a weighted sum of the impulse responses. We can also extend this to an integral and a 2D function. So that we'll go through this a little faster because obviously, we just want to take the intuition we got from our discrete function and just apply this and just say, well, in the limit, sum's going to become integrals. And so here we have a double integral of the shifted Dirac delta functions with the weights. And the response is going to be given by now this double integral of these impulse responses multiplied by those weights. Okay. So once again, we have our responses, just a sum of impulse responses. Right. And now it's in 2D and in integral form. Okay, so that's really applying linearity. So linearity allows us to apply superposition. Okay, so in this class, we typically focus primarily on what are called linear space invariant or linear shift invariant systems. And so we've talked about linearity. Now we're going to talk about space invariance. And what does that mean? The system is space invariant if the impulse response depends only on the difference between the output coordinates and the position of the input. So previously, remember, we had these input coordinates, the object coordinates, and we have these output coordinates, right? And so the idea is if my impulse response just depends on the difference between those coordinates, then I have a shift invariant system. So this is an example of an impulse response where if I shift my impulse from the top left corner to the bottom right corner, then my output shifts by the same amount in the output coordinates. All right, so if that's true, that's a space invariant system. Another example, if you think about 1D, a time invariant system would be something similar to if I had like, let's see. Okay, so let's say I have this bowl here, right? And I hit the bowl, right? And it makes a sound, right? Now, assuming I hit it the same way with an impulse, that each time I hit it with the same impulse, if the response is the same, no matter when I hit it, then that would be a time invariant system. Okay, so to first order, we would assume that this is time invariant. If everything is the same and I hit it, each time I hit it, I should get the same output. All right. So the nice thing about linear shift, and now we're going to combine linearity and shift invariance, and we're going to see how this is really powerful. Because let's say this is my input here on the top line, and let's say the impulse response, the response to this impulse here is given here. So let's say this is delta of x, right? And this is my impulse response h of x, right? So we know that the output, so this is my output down here to my system. One of the parts of my output will just be my impulse response because I did have an impulse in there. But and let's say this is 1, 2, 1. So now this is going to be delta, like 2 times delta x minus 1, right? So the shifted delta function. So this is h of x, right? And this is going to be h of x minus 1. It's just shifted. We shifted the input by 1, so we shift the output by 1. So that's shift invariance. We multiply the input by 2, so we multiply the output by 2. That's a scaling property of linearity. And then the last part is we have this. This is delta of x minus 2. So that's going to give me an output h of x minus 2. So we can write out these different, oh, sorry, this should be 2 times that, right? 2 times h of x minus 1. And then if we sum up all this stuff, so let's say we summed it up and got something like this, then the output would be the sum of all those weighted and shifted impulse responses. All right, so that's basically, if you have that intuitive picture of linear shift invariant systems, that's really all, most of what you need for this class in terms of linear shift invariant systems. Okay. So what that allows, that leads to what's called convolution. So convolution is just a very fancy name for what happens when you have a linear shift invariant system. So we saw this before. We have our input. Let's actually go to here. I'm just going to follow along here to because we're running a little short on time. Let's see. Okay. So this is my input. Okay. And as you can see, it's basically a weighted sum of Dirac delta functions. Now, the only thing I've changed here from superposition is previously we already had this, the linear response to a shifted delta function. Now, and we had this general terminology here before, h of m prime k. Now, the only thing I'm saying is due to shift invariance, I can say this. Okay, it's just, that just means if I shift my input, my output, if I shift my input Dirac delta function, then my output impulse response is just shifted by the same amount. So that's all we mean by shift invariant. So everything in this derivation is the same up to here, right? So we've done this all the way here, and now we're just saying from going from this line to this line, we can say that the response here, for example, the response L to my shifted Dirac delta is just my impulse response shifted by that same amount. Okay. And this allows us to write it in this very special form that my output to a linear shift invariant system is just the weighted sum of shifted impulse responses. So all I need now is one impulse response. I don't need many impulse responses. I just need one impulse response. And I know that I just have to shift it around, scale it, and then add them all up. And that's going to give me my output. So that's a convolution sum. All right, so that's important concept to have. Okay, so in 1D, we can just make the summation an integral, and then we also have to, have a d xi here. So the form is the same. I have g of xi, h of x minus xi. Okay, so I have some sort of, we're integrating over some input coordinate xi, and we're measuring an x's. So the xi's are representing sort of the different shifts of my impulses, and then the x is what I'm measuring. Okay, so for any given location x in my image, that's going to be made up of the contributions from a lot of different impulse responses that sort of project onto that location x. And we have a special notation. We use this asterisk to represent convolution. So this, we write this as G convolved with H. Now, an extremely useful fact. So one fact, probably one of the facts that you will want to use more often than not in this course is if I take any function G of xi and convolve it with a shifted Dirac delta function, that just shifts my function. So that's a very useful thing. Basically, anytime I want to shift a function, mathematically, I can just describe it as convolution with a shifted Dirac delta function. Okay. So for the remaining part of this, we have about 15 minutes. Yeah, so we should have enough time to go through some examples of convolution, and then we'll plan to stop there. And if people want to have more questions, we can do more, but otherwise we'll leave Fourier transforms to next session, because I think this is already quite a lot for one session. So here's the idea. We're going to unpack this convolution integral a little bit. So what does this say? It means take my function G of xi, right? And let's say I have some function, H of xi, right? Well, this means I have a minus xi here, right? So that means I'm sort of flipping it and also shifting it, right? Because I'm having this x, I'm adding this x to it, right? So I have to take one of the functions, and it doesn't really matter, as Dr. Mavet talked in class, it doesn't matter which function you flip or shift, it's the same. But one of the functions, you take it and you flip it around its axis, and then you look at what happens as you shift it, okay? for every shift, right, because we're integrating over xi, you basically imagine multiplying the function, right, and then integrating the product over all those shifts. Okay. So in this case, the shift is by x, right? So basically, if I want to know what my value is at x, I basically take my one function, g, take my other function, flip it and shift it by x, multiply those two functions together, and then integrate the product. Okay, so let's see what that looks like. So let's start off with an easy example, which is we just said that if you have a rect, so this is my rect function, rect of x, right? And I'm convolving it with a Dirac delta of x minus 1/4 delta of x plus 3/4, right? And we just said that one of the more useful things is this thing, that if I convolve for any function with a shift Dirac, I just get g of x minus that, x minus delta. So let's see what this means. That means rect of x, okay, if I convolve it with that thing, I'm going to get rect of x shifted by 1/4 plus, using linearity, rect of x shifted the other way by 3/4. Okay, so that's all that is. So that's, we can write down what that looks like. I know one rect will be centered at 1/4 and the other rect will be centered at minus 3/4, right? And I know it's going to go out to a half, so that's 3/4 and minus 1/4. So one of the rects is here, and the other one is minus 3/4, and it goes out to half, so the minus 1/4, and it goes out to minus 5/4. So it's here, right? So this is this guy, and this is this guy, right? And so my output is just this. This has width what? The width of this is 2, right? So this is just equal to rect. It's centered at minus 1/4. So this can be rect of x plus 1/4 over 2. Okay. So this is a simple example, but it's actually getting into some things where we're using two things. One is it's giving you experience in sort of shifting functions. And it's also giving you some practice in saying, you know, how do I write, you know, if I see a function like this, how do I write it in mathematical notation? Okay, so in this case, the key was the bottom of this is always going to be the width of the rect function. So that's 2. So I can just know that 2. And then this thing here is just given by x minus the center of the rect function. Okay, so that's x plus 1/4. Okay, so here's a more complicated example, which I think is the last probably we'll do for today. Let's see how we're doing on time. Yeah, we have enough time to do this. So this is a very classic example, which is I'm going to take rect of x and convolve it with rect of x. And the question is, what does that look like? So you can imagine, if you think about it, you want to think about it first. You can take one rect function and you're going to take the other one and flip it, but flipping it just still a rect function. And then as you shift it to different locations, you want to multiply and integrate. And we're going to go through that together and see what that looks like. Okay, so basically we're going to, here we've got g of xi, so that's going to stay the same. And then we're going to look at h of x minus xi for different values of x. Remember, x represents how much you shift things by. Okay. So here we have at x equals 0, right? This is x equals 0. There's no shift, right? So it's just basically the rect function. And now when we multiply these two rect functions by together, we still get the rect function. And we look at the area under this multiplication, the area is just 1, right? Now our shift is x equals 1, okay? So we have h of 1 minus xi. So that means we're going to shift it over till where xi equals 1 is the center. So the center, it'll be centered at 1, okay? And so these two things, this thing here And these two things don't overlap, right? So when I multiply them together, I get 0. So the area of that multiplication is 0. Next thing I'm going to look at is when x equals 1/2. That means I just take the rect function, I shift it so it's centered around 1/2. And now if I look at these two things, they only overlap between 0 and 1/2. So this is the overlap, right? Okay. And the area of that overlap is just 1/2. Okay. So if I did this, if I can imagine, so what I've done here is, so the function of x, I know at x equals 0, whoops, sorry about that. I get 1. And at x equals 1, I get 0. And at x equals 1/2, I get 1/2. And so I can imagine if I just did x's in between, I would just get, a linear function like that. And then similarly, since it's symmetric, I could go the other way. And so the convolution of two rect functions is just a triangle function. And we actually, this is so important, we actually give it a name. This is lambda of x, so a triangle function. All right, so that's a simple example of 1D convolution. I think for the last few slides, we're just going to talk about 2D convolution. So obviously for imaging, we have to think about 2D convolution, but to do it by hand, we just did a 1D convolution by hand, and to do a 2D convolution by hand, it's just, it's really hard. It's just a lot of algebra. So typically we're going to just do that using MATLAB or let the computer do it for us. But the idea is the same, that we basically have one function and we're multiplying it by shifted and flipped versions of another function. And we can write that as this, where this can represent 2D convolution. But oftentimes we'll just use one asterisk because it's sort of obvious. If I have a 2D function and another 2D function and I convolve them, it's just going to be, we'll assume that's 2D convolution. Okay. So what's a 2D convolution example? The simplest one is, once again, if I have some function rect and I multiply it, I convolve it with shifted Dirac delta functions. So if I convolve by linearity, I can think about taking this and convolving it with the rect function. That just leaves me a rect function here. So it's not shifted at all. And then when I convolve it with this guy here, this is going to shift my rect function over to here. Okay, it's going to shift it over by 1/2. So if I look at the area and then I sum them up because it's linear, so this has value of 1, 2, and 1. So that's what my output looks like. Now, the example that you're doing, I think you just did for your homework, which I guess is due tonight. So it's probably good to go over that. So this is the last slide I'll do for this part. Is so this is my, let's say this is my cross h, let's say some function g of x, y, and this is my impulse response h of x, y, right? And this is the convolution g convolved with h. Okay. So you can think about, one way you can think about convolution is this is just, this cross, right, is just made up of little impulse responses, right? So I can replace every point in this cross with this impulse response, right? So if I think about replacing every point in that cross with this response, and I add them all up, I'll get a slightly blurred version of my cross, right? Whereas here, if I replace every point in my cross with something that's has a bigger width, then it's obviously, whoops, sorry. It's going to actually result in a more blurred version of my cross. Okay. So yeah, so there's a question for the homework. Does the h of x have to be centered on the figure? That's a good question. Let's see how the homework was worded. First of all, does anyone know off the top of their head how the homework was worded? Let me double check that.
I think so, because it says that the Gaussian functions should be centered in the middle of the 11 by 11 matrix. So I'm guessing that.
Yes. Okay. Generally, yeah. Okay. So if it's h, yes, then yeah, that would be centered. Yeah. Typically, because that way, then you're not. If it wasn't centered, then you're going to end up with a shift of your cross, which typically you wouldn't want to do if you're just blurring. So yeah. Typically in image processing, if you're just trying to blur something, you want to make sure that your blurring function is symmetric around the origin, because if it's not, it will end up shifting your image as well. So that's a good question. Okay, so we're almost to the end of the session. So let me just open it up if there's any more questions, or if people want to have any, want to see something about Fourier transforms or have any questions about that. I know Professor McVeigh touched upon that this past week. They will be somewhat important for CT, but Fourier transform will be even more important for MRI, but we'll have a session 2 weeks from now that will go into more depth on the sort of Fourier transform theory that will be important for the MRI part. Okay, so are there any questions or requests before we end this session? Let's see, open up the chat.
I had a question for homework
Sure.
too.
Sure.
So in the first question, you have to go over linearity, and in the book, they do like the sum of the function. I was wondering if you wanted that for the solution, or the way we did it today, where you like split it into like G and H and then add it up and verify it like that.
Which problem in the book is it?
Give me 1 second. It's 2.6.
Okay, let me look at 2.6. Determine whether the function is linear. Yeah, so basically, the way you can do it is you can always put in, I mean, you can certainly show, I think that as long as you show that you're applying addition and scaling, that will be fine. So for example, if I assume a function g of xy gives me some f of x minus 1 plus f of 0 xy, and then I have another function h of xy, and then I add them together and see what I get, and then compare the addition to what happens when I put them in separately and see if that's equal. So basically, you would still, for part A, you're still checking both addition and scaling.
Okay, so doing like the 2-step like we did today, it's fine. Because on the book, I think it's page 27. The way they do it is like, I think they do like both together. They do the summation and the scaling in the same process kind of thing.
Yes, you can certainly do it that way.
Okay.
Whatever way works for you. I mean, I like to, when I'm teaching, I like to break it into two just to make it more clear. But if you're very comfortable doing it all in one, that's also fine.
Okay, perfect. Thank you.
Yeah, sure. Quick logistics question. Homework is due. I think we have, let me double check, but I believe the assignment has been changed to be due at midnight, 11:59 p.m. tonight. So I believe due to sort of multiple people requested that. So going forward, the homeworks will be due at 11:59 p.m. on Fridays. Okay, any other questions before we end this session? Okay, if not, let's end this session. And if there's questions, I will post the annotated notes later today. There will also be a recording of this session on YouTube posted later today. And if you have any questions in the meantime, feel free to either ask me or Professor McVeigh. And then if you have requests for the next supplementary session, please let me know. I mean, we want to try to gear these sessions to what's helpful to you, but if there's no request, essentially, I will just be going over the basics of 1D and 2D Fourier transforms and their properties. Okay, let's see. Yep, submit on Canvas, that's right. Great, thank you all, and we will end this session. And have a great weekend, thank you.